Okay, I'm going to kind of okay, let's start. Skip a few steps, so maybe do a little bit of in colonies too. Okay, so we discussed how by creating these meta-experts we can create an algorithm with a guarantee of this form, but it's quite inefficient because it depends on creating these meta-experts. And there's these meta-experts are exponential in k. And in fact, we now have an algorithm that depends on k. I'm not going to derive this for you, but basically it turns out that we can do well by adding an additional update. So we have the same update as before where we update the loss, maybe we normalize the loss also, doesn't matter if you normalize or not. And then what we essentially do, I'll demonstrate graphically, is each expert reduces its weight by some fraction, 1 minus alpha, and then shares it with the other experts. Let's look at this graphically. And then have a slightly more complicated update if we want to prove a slightly improved thing. But roughly what we're going to do then is that all these experts, we have the normal loss update, okay? But then we still want another expert to do well. So each expert kind of shares its belief in itself with all the other experts. So expert 3 takes whatever its weight was, gives alpha n minus 1 of it to each of the other n minus 1 experts. We can make this proportional to loss for an improved bound, but a simple way to understand what's going on is each expert simply shares some of its weight with each of the other experts. So let's. So what can we prove then for that update without going into the details of the proof? Because the punchline is going to relate this to a genetic algorithm. We have some sequence of k experts. I mean, we're going to compare to a sequence of k experts. K will be the number of shifts in that sequence. So if I1 is equal to I2, there won't be a shift. But as soon as we have two experts which aren't the same, we add 1 to k. So k is the number of shifts. The loss of the sequence is just we define this loss over a sequence of experts. Let's ignore this variant to the bound for now. Suppose that previous algorithm where we share some of the weight with each of the other experts. We share a weight that's k over L minus 1, which we can think of as being the probability of shifting on a given trial to another expert. Then we can prove the following bound for an efficient algorithm. Okay, and the bound kind of makes sense from an information theoretic perspective because we're doing as well as the loss of the best sequence of experts, and then we pay how much it costs to code the sequence of experts, i.e. we need to code the first expert, so we pay log n for it. We code its number 1 through n. It costs log n bits. We only need to code n minus 1 position for the remaining n minus for the remaining k shifts. So we code those k log n minus 1. Now we have to code where those shifts occur in the sequence. Those shifts, how many bits does it take to code where something occurs in the sequence? Well, if there's k shifts and there's L trials, that's roughly k over L is the average distance between each shift. And so you can imagine it takes k over L bits to code in some code that tells us how much more we need to do at k times. I'm arguing loosely here. Okay, to pull out information theoretics side more carefully, I could discuss this, but I don't want to. Okay. So we get the bound for the previous algorithm. We're just going to show you that it works in some sense. So here's just a toy simulation. So here we have some 800 trials. We have 3 experts, 3 shifts. The number of experts is 64. Our loss function is a square loss. Eta, our learning rate was 2. This alpha parameter is set to 0.024. So I did this by sampling uniformly at random, probably from 1 over, I don't know what I did, but I did from some sort of uniform sampling so that a typical expert was designed to have 1 tau loss on average per trial, whereas the best expert would do much better and have expected loss of 1 over 120. I can't remember the exact parameter of the experiment, so I generated that. But now we can look at the performance of these algorithms. So let's explain what I'm plotting. So this axis is the amount of loss. This is the number of trials. So I'm plotting the cumulative loss over time. So let's look at the bounding brackets here. The loss of the best partition, i.e. if I knew the best expert from 0 to 200, and then I knew the best expert from 200 to 400, this is this loss rate of 1 over 1/20th per trial. So, this is at 800 times 1/20th roughly. It's a random thing, average. So the best partition achieved this loss. If I took some random expert, it's achieving loss 1/12th per trial. So, roughly, the expected loss of a random non-best expert was that. Okay, so these are the kind of the 2 bounding things, and we hope that we can have an algorithm that does well. Okay. I plotted 3 algorithms. Let's only worry about 2 of them. But the first thing to observe is, so the 2 basic algorithms I compared is an algorithm without this sharing update. And here, this is an algorithm with the sharing update. Okay, without share, with sharing. So what we saw is both the sharing and without sharing algorithm did quite well up to trial 200. They're all doing better than a random average expert. They make some loss in the beginning, but then they kind of figure out what's what, and they're doing as well as the best. Then from trials 200 to 400, they start out, they're both not doing so well, but the basic expert algorithm without this sharing update basically starts to make loss linearly at the expected loss rate. Whereas the sharing algorithm, depending which variant you used, either the fixed share or the more sophisticated variable share, basically starts doing pretty well. Its rate is roughly that rate, and then when things shift again, it gets confused, but it basically tracks the sequence, whereas the pure exponential update doesn't track the sequence. Okay. So we can learn this sequence of experts. Yes.
Could you try to repeat how the sharing update works?
Yes. So I'll write it on the board, and I'll let you. I interrupted you. Okay, so the algorithm consists of 2 updates, and I'm going to slightly simplify from what's written in the notes. So the first update was WTI is equal to WTI e to the eta. The loss of that, I'm simplifying the notation, the loss of that expert on the trial, and then we normalize this, so things look like a probability distribution. This is the first update, and this corresponds to the general expert update thing, which you did in supervised learning. Now we're going to add an additional expert, so our algorithm is more adaptive based on some parameter alpha. The additional update, which we do after this update, is we then further change it so WTI is equal to, and slightly different than what I wrote in the notes, but you know, I'm just simplifying or leaving out unnecessary details. It's equal to its old weight. We do a convex combination. It's equal to its old weight. It's equal to its old weight, but then it gets WT plus 1. It's equal to its old weight, plus it gets a fraction alpha of the weight from each other expert. So summing over k not equal to I, there's n minus 1 other experts. So this is k not equal to I, W, T, K. Is that correct? That's correct. So each expert, what happens is we do this loss update. And the sharing update is we remove a fraction 1 minus alpha of its weight, and we get from every other expert a fraction alpha n minus 1 of their weights. And so that's kind of what this graphic is supposed to be visualizing. Each expert keeps 1 minus alpha of its own weight, and it gets alpha n minus 1 of its weight from everybody else. Did that clarify?
And what is then the difference between the fixed and the variable?
Okay, so I avoided describing that before, but I will describe it since you asked. The difference is now here we gave a fixed amount to weight, but you know, suppose an expert is doing quite well. If an expert is doing well, intuitively we don't want it to share its weight because it's doing pretty well. Okay, you know, as long as it's doing great, it probably shouldn't share much of its weight. Whereas if it starts making loss, then maybe it's time for it to start sharing its weight. And that's exactly what this update does now. So now the given expert keeps 1 minus alpha of its loss. It essentially keeps, you know, when you linearize this, it keeps 1 minus alpha L approximately. So if it makes 0 loss, it keeps 100% of its weight. If it makes loss of 1, because our loss is scaled to 1, then it keeps 1 minus alpha to the 1. It gives up alpha of its weight. Okay, so now we scale the amount of weight it gives between 0 and alpha smoothly with respect to its loss. And so if you do that, that tends to have better performance. What else do I have to say? It has better performance, but you have to. This is more complicated to explain. And the bound no longer depends on the sequence length, right? So if right now I put in sorry, you ask a question, you get probably more than you want. But here, this depends on the sequence length. Ideally, this would depend on the loss of your partition. And if you use the variable share algorithm, this L minus 1 gets replaced by L star, which is going to be smaller here. And so it has a sharper bound, or an improved bound. Okay. We can intuitively understand what's going on by looking at the weights. So this first plot is I'm showing a plot of the algorithm which does not do the second update. If we don't do the second update and we only do the first update, we can kind of see how things go wrong. So what am I plotting? I'm trying to plot 64 different weights in MATLAB. So this is the scaled value of the weights. This is the number of trials. So in the 0 trial, these are all about 1 over 1/64th. But rapidly, you see one expert, this best expert's weight improves very fast, because everybody's taking loss, everybody else's weight is decreasing exponentially. So you very rapidly learn the first best expert for the sequence between 0 to 200. But then what happens at trial 200? At trial 200, you have this problem. You have the fact that, what happens at trial 200? This best expert has a very large weight. Somehow, you have to learn the weight for the new best expert at this time to predict well. So what happens is that new weight starts going down. It goes down, 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 but it's still relatively much larger than everybody else, so you can't really tell in this plot that it's going down. And in fact, it's not until you're getting pretty close to the 400th trial that you begin to see the effect of the change. Even though it's actually in exponential terms, it's exponentially kind of relative-wise going down quickly, but basically by trial 400, it finally starts to learn the new best expert's weight at trial 400, but then it's too late. Because now we need to start learning another new best expert, okay? And so this large weight here is the weight of the expert that was good for trials 2 to 400. It's a little bit things that, then we have the same problem. It needs to start unlearning again around 600. So this is what happens if you don't have this secondary update. So now if you add in one of these updates here, I've added in the variable share update, you see instead plotting the scaled weights the best expert is the difference is you look at this as its weight never kind of makes it all the way to 1. And it's kind of designed so that it can quickly unlearn. So when it gets near trial 200, it actually manages to go down quickly and switch, whereas the other one never managed to start going down until enough to change the value of the predictions until trial 400. And so you pick up the new best expert each time eventually, and this corresponds to these plots you see here. We're picking up the new best expert. There's a lot of applications for this algorithm now. This is another slide. Okay. Now I want to think about genetic algorithms for a moment. Before I think about genetic algorithms, I want to point out this online learning scenario is actually what, maybe not precisely the scenario, but when Holland came up with the genetic algorithm, he was interested in, at least in his description, of not precisely applying this to an optimization algorithm, but rather to an online adaptation setup, for instance, like the bandit problem. I.e., the idea where you get a sequence of things over time and you're constantly shifting and adapting. So this idea of applying an evolutionary algorithm to an online setting is quite old. I'm going to go through this part faster until I get to the punchline, I think. I don't know, for the sake of notation, this isn't a big deal, but I want to slightly change the loss from the square loss to the following loss, where we imagine that each of these algorithms correspond to action. So you have expert n, you have expert n minus 1, you have expert expert 1. So the experts kind of correspond to a row, like you're playing a game. You imagine that there's some, for instance, loss matrix, and nature, the environment, chooses a column, okay? And the loss that each algorithm receives, each of these individual experts corresponds to the column. So this expert would receive 0.3 loss, this would receive 0.1 loss, this would receive 0 loss, this would receive 0.7 loss. Okay, so in this case, we would like to have chosen this column. Turns out, up to the change in notation, this expert algorithm that we've described is good for this scenario. Once more, we do the same thing. We set expert weights uniformly to 1 over n. And now the way we're going to predict is we're going to just predict the weights of our experts. Okay? And then the loss that we occur, it's imagine we're playing a game. So it's just like when you play Prisoner's Dilemma, rather than saying cooperate or defect, you put a probability vector. You say I play cooperate with 80%, defect with 20%, for instance. And then either you measure your loss as a mixture loss depending upon what the opponent does, you compute that mixture, or you simply imagine that if you play cooperate or defect with 80%, 20%, you draw a random number sampling from 80 to 20%, and you experience expected loss of that. Okay. We do the same update as we did before. Each expert, which we imagine corresponding to an action, gets its weight decreased by this quantity, and we normalize the weights so things sum to 1. So what we're doing now is, the way we set things up is we receive a loss, and we give this weight vector. It's like we're playing a mixed strategy. If you play rock, scissors, paper, optimal mixed strategy is to choose 1/3, 1/3, 1/3. So if we can choose mixed strategies, we play the mixed strategy. If we can only play a pure strategy, we just sample to choose an action. In that framework, we get a similar type of bound. We get this extra term, L star being the loss of the best mixed strategy. Okay, but I'm not interested in that part. So I'm interested in thinking about this as an evolutionary algorithm. So now, okay, let's imagine a GA without crossover. So here's some notation. We're going to do roll-up wheel selection. S will be our population size. N will be the number of types of individuals in our population. So imagine if you had a bit string, length k, for instance, then you would have 2 to the k types of individuals in your population. Okay, so S is the population size, N is the number of types of individuals. Ci will be the number of individuals of type I in the current generation. C prime I will be the number of individuals of type I in the next generation. So if we have a fixed size evolutionary algorithm, the sum of all the number of individuals of each type have to sum up to the total population size. We'll call Fi the fitness of an individual of type I. Okay? So doing roll-up wheel selection, the probability of selecting a particular individual of type I is just its fitness divided by the total fitness in the population. You know, we could write this as the probability of instead of saying particular, I could say any individual of type I and add a proportion of CI in the population. Okay, questions so far about the notation? Okay. So what's the expected number of individuals of type I in the next generation? So now we're analyzing our GA, and there's only selection. There's no mutation. Okay. I claim that the expected number of individuals in the next generation is just CI times PI times S. Why is that? So just roll at wheel selection again. We remember the number given a particular individual, its fitness is its number of individuals corresponds to its fitness divided by the mean fitness. I guess an easier way to see this is, so for individual, so CI, so suppose we have CI individuals of type I. We take one individual of type I, what's its probability of being selected? Its probability of being selected is just, am I doing something wrong here? Yes. Each individual CI has PI probability of being selected, and if there's S selection steps, just multiply them together. I'm not explaining this. Is equation 1 clear, or should I develop this more? So if we have a single individual of type I, the number of individuals that we expect of it in the next generation is its probability of being selected times S. If we now have CI of them, it's just CI times PI of S. Okay. Now we'll go ahead and the probability of being a particular individual being selected is just its fitness divided by the total fitness in the population. Now we'll go ahead and we'll set the fitness of an individual. We'll make this a definition. We'll say its fitness is e to the eta li, and we'll substitute in. So if we substitute in e to the eta li, we simply get this. Now suppose we divide both sides by S, we get Ci divided by S is with the S on the other side here. Now we then go ahead and we define Wi to be Ci divided by S. We get the, substituting in, we get the expected value of Wi to be Wi times e to the ALI this. Now suppose we let S, the number of individuals, go to infinity, then we get exactly our expert's algorithm update. Its weight is proportional to the loss of the other experts. Now, when you did a simple GA, the way you did mutation was, you flipped a bit for every thing on a bit string. But imagine that we could imagine doing the following kind of structuralist mutation operator, where what we did to mutate was each individual could change into any other potential individual with uniform probability. Okay? So that's exactly this. Each individual either stays itself with probability 1 minus alpha I, or with probability alpha, it switches into another individual, and the individual that it can switch into is uniformly selected from all the different individuals. So there's no structure to the individuals anymore. Okay? So mutation gives us the share update. And you can think about in a real population, this makes sense. If you want your population to be adaptive, you need some form of mutation, because first one thing is good in the population, but then things will change over time. So by looking at the GA in the infinite limit, we get the share algorithm. If we have structureless mutation, and we don't have crossover, and we have selection. Okay. Let's do something different. Okay. We don't have much time, but so evolutionary computation is more generally part of natural computation, where people have lots of biologically inspired algorithms. And I think one thing common with all these biologically inspired algorithms is, by and large, they're algorithms that somehow, or the underlying algorithm design type is somehow, you're looking at collective behavior of a large number of individuals. So we have a little video interlude. So I don't know how well you can see this. This is a nice graph randomly from YouTube.
They're coming back together. It's almost like they know the design they're creating. Oh, look. Oh, good.
Okay.
Now it's like chasing.
So
Drop down. Yeah.
So just like for genetic algorithms, people were kind of inspired by evolution to create algorithms. Another area of natural computation is the idea of building algorithms that are inspired by swarms of individuals, and building algorithms based on the collective behavior of swarms.
Look at that. Oh my God. Right there, you get that?
So So people have been inspired by swarms of behavior. As you can tell, these two were very inspired. Perhaps they went home and they decided to create some algorithms. Like you, maybe. You can create your own swarm algorithm. Okay. I of course lost my slide. Okay, I'm going to go through some of this really fast. And the only part of this I really care deeply about is perhaps the ant colony part. So it gives you a nice algorithm that works. The other stuff is a little bit, I guess for me today, a little too wishy-washy. Sometimes I'm in a different. Okay, swarm intelligence. Sorry, you can't see what I'm doing. I can see what I'm doing. Okay. People inspired by swarms of individuals and trying to create algorithms based on the behavior of swarms. Key thing about swarms is that the individuals seem to act in unison. They do various things in unison, but it's not like they have a centralized controller. It's each individual making individual decisions. People have used this to produce pretty computer graphics. By having rules of movement, they've used it to produce optimization algorithms called particle swarm optimization, for instance. I haven't seen this work very well, so I don't think particle swarm optimization is that good. But it has been an idea. I'm not going to do the particle swarm optimization because I think ant colony optimization works pretty well, and I'd rather do that in the remaining time. Okay. You can kind of take these swarms and kind of define perhaps some qualitative ways to explain how swarms work. Somehow the individuals have to interact. You can have some interesting behavior if there's positive and negative feedback based on their behavior. You can classify swarms in this way. I'm not going to focus on this. Peter Bentley, who these slides are based on, who's a lecturer in this department, has a nice book on this. Ant colony optimization. I've given you a copy of the paper. In other years, I've given ant colony optimization as an assignment. It's been applied to many types of optimization algorithms, optimization setups. Happens to work fairly good on the traveling salesman problem and similar problems. It's become quite a popular area. And you can vaguely see these as algorithms inspired by swarm-like behavior. A bunch of individuals working together as a unit, behaving independently. Okay. Before I do that, just to give you some pictures of interesting self-organized behavior before we get to ants. Here's a picture of a termite colony. Now, as far as we understand termites, we don't believe that there's a smart termite who goes, okay boys, this is what I want you guys to do. I want you to first put the birthing chambers over here, the food chambers over here. There's not like a manager termite or a class of manager termites. There might be a breeding class, but the breeding class doesn't seem to correspond to a management class. It is a way. So termite colonies are often given as an example of self-organized behavior. I've written down some facts about them, which I think I have time to tell you. Termite colonies, 30 feet high, They're quite sophisticated architecture on the inside. There's a cooling duct. There's a chamber for where the queen gives birth to things. There's around that chamber. There's nurseries where the children are raised. There's an area where they store food in there. They also farm fungus in there. So they have a whole little termite society, but any sort of intelligence doesn't seem to be in individual termites, but somehow distributed collectively throughout the colony. Okay, we're doing ant colony optimization. Well, probably many of us played with ants when they were children and have seen ants form paths. This is another picture of some. This is a picture of a swarm of army ants. Army ants can be some 500,000 to 20 million ants in one of these swarms of ants. They can go out on raids, which take place over 15 days. The actual distance that one of these large moving army ant colonies can be some 200 meters long with a front of 20 meters. Well, they feed on other small insects. Usually this happens when we have a new queen and the colonies want to switch off. So we have one queen going one way and one queen going the other way. A lot more known about ant colonies, but people have seen these complex insect behaviors, and so they've been inspired. Oh, we use some of these ideas, understanding the way insects work, to build optimization algorithms. You're all familiar with the traveling salesman algorithm, so let's see how we can potentially be inspired by ants to solve the traveling salesman problem in an approximate sense. Okay. I don't know how well you can see this, but so imagine you have ants out foraging for food. You may have observed this type of situation as a child. If you were me, or some of you probably did experiments like this. Here you have a bunch of ants, and there's some food over here, some food at location 1 and food at location 2. So you have some river or hole that separates the colony from the food source. Oh, I am going way too slow. Okay, there's two ways for these ants to go. There's a short direct way or a longer, less efficient path. Even though ants don't seem to be intelligent from a biological perspective, it's clearly bad for them to take the longer route. They should take the shorter route as much as possible. But how can ants decide to take the shorter route? How do you think they do it? Yes?
Trial and error, and that one who gets back just marks with pheromones the track. So
yeah, so there's no intelligence. Exactly. So you're describing exactly what people have confirmed experimentally with real ants, and they take the shorter path. Why would they choose to take the shorter path? Well, what you imagine is ants actually take both paths at random. Okay, so they go there and they go back and they get some food. If nothing else happened, and the paths aren't intelligent, and ants aren't intelligent in telling one ant to take another route, why do they end up on the shorter thing? Well, what's been observed is that ants, as they're going out foraging, mark their route. They mark their route with some sort of substance with a scent called a pheromone. And the observation is, if you're laying out that pheromone at a constant rate, even though initially ants are choosing each bridge at random, if an ant biases its route to choose a route where there's more scented substance, well then they'll naturally end up choosing the shorter route with high probability, because observe, if an ant takes the shorter route, goes there, gets food, and comes back, that means more pheromone can accumulate there faster than than taking the longer route. So as this pheromone accumulates, the shorter route is then taken. So this is how ants manage to choose a shorter path by doing this. Okay. This is what I said. Okay. Given this inspiration, Dorigo and I forget the other person right now came up with an algorithm based on this idea. Finding shortest paths is an easy problem, but maybe you can think of that as a useful thing that you still want to be able to do in solving traveling salesman problem. So in essence, in the 2 minutes remaining, by simulating having some, where you can imagine doing the traveling salesman problem, where ants take different edges in a given network with probability higher according to its shortness, which corresponds to the accumulation of pheromones. So basically, with some loose inspiration by the way ants work, the idea of ant colony optimization is you drop a series of ants on your traveling salesman problem and use it to solve the TSP problem. I'll go through this very quickly, so I can do this in a minute. Okay, ants explore at random, but how do they explore at random? They explore by this. Let's ignore this part. What are these two quantities? These quantities are tau and eta. Tau corresponds to the intrinsic preference to take this edge in your tour. Eta corresponds to the amount of pheromone. Actually, S is what we care about. The way they select is, if you do this step, is you say the fitness of an edge corresponds to its intrinsic shortness plus the amount of pheromone on it. You do roulette wheel selection on that. Beta is some trade-off parameter, and you choose, the ant chooses an edge to take based on roulette wheel selection based on the amount of pheromone and its intrinsic shortness. Otherwise, you flip some biased coin and maybe you do the greedy choice and you choose the best one first. So that's how ants choose edges. This is the roll-up wheel selection I was mentioning. You do some updating, global updating for the best possible path. You let pheromone decay over time. So you update for the best possible path. You let pheromone decay over time. You put these together. If you go ahead and implement it, you'll find out this is a much easier to tune algorithm than your GA for those problems given in your coursework. And this is my summary of ant colony optimization. Okay, questions? Okay, have a good weekend, and you will see Chris next week.
Only